So theorem, if we have a sequence of holomorphic functions, which means complex differentiable on an open neighborhood of any point on the domain that converge uniformly on f to d, then the limit function is holomorphic on d. Ooh. So we preserve complex differentiability as well. Let's see here, how do I do it? So we're going to use Morera's theorem. Remember, Morera's theorem said that if the integral around an arbitrary closed rectangle, what other kind of rectangles are there? Arbitrary rectangle with sides parallel to the coordinate axis, if that integral is 0, then that implies holomorphicity of the function in that domain. So we're given that these integrals are 0 because we're given that the jth component function is holomorphic. So by Morera's theorem, these are 0. Or if you like, don't even use Morera's theorem. By Cauchy's theorem, we have a holomorphic function. We're integrating around a loop 0. So this is the 0 sequence. Its limit is a 0. On the other hand, because these are uniformly convergent, I can pass the limit inside the integral, like so. And then, by definition, the limit of the sequence is f. So we have the integral around an arbitrary rectangle in the domain is 0. Therefore, by Morera's theorem, the limit function is holomorphic. It's just saying what I just said. So the uniformly convergent sequence of holomorphic functions is holomorphic. Oh, but there's more. If you have a holomorphic sequence of functions that's holomorphic on a disk of radius r centered at r, and suppose the sequence converges uniformly to f on that disk, then for each r less than r, and for each m greater than or equal to 1, the sequence of complex derivatives converges uniformly. Well, the sequence of the mth derivatives converges to the mth derivative of the limit function. So the derivatives converge to the derivative, the second derivatives converge to the second derivative, the third derivatives converge to the third derivative, and so forth. We saw in the real case that this was not the case if the function is not uniformly convergent. Again, this is a theorem which is easy to prove as it's done down here in the complex setting. In the real setting, this theorem is not true. It's not enough to know that you have a sequence of uniformly convergent real functions which are differentiable. That does not imply that the derivative sequence converges to the derivative of the limit function in the real case. You actually need more data. It's annoying, but it's true. But that's outside the scope of this course. I'm just telling you that this theorem is special and a beautiful result of complex analysis proper. It's not just larger analysis, it's just complex. And the reason partly for that is the use of the generalized integral formula in the proof, because this theorem is only available to us in complex. So here's the proof. If we have a uniformly convergent sequence of functions, then we can pick a worst case estimator for it, all right? And so then I fix an S that's between R and R, like so. And I apply the Cauchy integral formula for the mth derivative of the jth sequence function and the limit function on the disk. And that gives me this lovely formula right here, m factorial over 2 pi I integral over the S circle centered at z naught of this contraption over here. But I also know that I can write the modulus of w minus z by adding 0 here, like so. And that is greater than or equal to the modulus of the difference of these two moduli, which by construction, this is equal to s. And this z minus z naught is at, I think is it equal to r, or is it, I think it's less than or equal to r. So, but if you think about it, if I'm subtracting a positive, a non-negative quantity, right? If I make this as big as it can possibly be, that makes this as small as it can possibly be, right? Yeah. So that as biggest it could be is r, so I subtracted that. Great. So with that estimate in mind, you then have that this difference is less than or equal to, so I was just working on the denominator up here, right? And this is greater than or equal to the denominator. So I'm making the denominator smaller, I think, by replacing this with that, which makes the fraction larger in terms of modulus. So this is bounded by that. Now this epsilon j, remember, is because of the uniform convergence of the sequence. We get the worst case estimator. But then, lo and behold, this will serve as a worst case estimator for the mth derivative. See, because the modulus of this is less than or equal to the modulus of that, which is bounded by that. But this goes to 0 as m goes to infinity, which means that, well, I'm glossing over some details here, but anyway, the argument is that we have found a worst case estimator for the mth derivative, which shows you, of course, that it uniformly converges. And that's what I claimed in the theorem. So, yeah. So all of this to say that complex series are very boring. They're very boring. Like, they behave very nicely if you have a sequence of holomorphic functions and they converge uniformly. Then the integral of the limit is the limit of the integrals. The derivative of the limit is the derivative of the limit of the derivatives. I mean, like, integration and differentiation converge with the limiting process for a sequence of holomorphic functions. This is what I was saying a bit ago. Normal convergence means that it converges uniformly on each closed subdisk contained within D. And that leads us to our final theorem for this section. If we have a sequence of holomorphic functions on a domain D that converges normally on D to a holomorphic function f, then for each m greater than or equal to 1, the sequence of mth derivatives converges normally to the mth derivative. So normal convergence is also preserved here. This normal convergence was introduced by Baer of the Baer category theorem. And here's what he said. He said, "In my opinion, the introduction of new terms must only be made with extreme prudence. It appears indispensable to me to characterize by a brief phrase the simplest and by far most prevalent case of uniformly convergent series. That of series terms that are smaller in modulus and positive numbers formed by a converging series, what we sometimes call the Weierstrass criterion. I call these series normally convergent, and I hope that people will be willing to excuse this innovation." So humble. A great number of demonstrations, be they in the theory of series somewhat further along in the theory of infinite products, are considerably simplified when one advances this notion, which is much more manageable than that of uniform convergence. So he's preferring normal convergence to uniform convergence. Yeah. Probably not. The categorical error. Yeah. Thank you. And that brings us to power series, which is where we'll start up next time. So basically, to summarize where we're going, a power series is a series formed by what? Power functions. Are these holomorphic? Yep. Are they? So then what that means then is wherever this series converges, it's going to pretty much converge normally. Anyway, so we'll see how that works next time. So I'm going to stop here for today. So thank you, guys. I hope I don't regret stopping right here. But anyway, that's where I'm stopping.